through a Matlab tutorial, which I call CMF's Cone Fundamentals and Cone Isolating Stimuli tutorial, that will expand on some of the ideas in the online or recorded lecture I gave on why the cone fundamentals are a linear transformation away from a set of color matching functions. Here we'll do it in code a little bit and then explore the ideas of cone isolating stimuli and color spaces a bit more. This tutorial is available in a GitHub repository, which is given here, github.com, brainerdlab/teaching code. And to run it, you'll need to have some other toolboxes on your Matlab path, the Psych toolbox, the Brainerd Lab toolbox, and something called the Color Book toolbox. Those are also freely available. If you use our toolbox, also available on GitHub here, you can install the teaching code repository in your toolbox projects folder, and then just type tbuse project teaching code, and all the dependencies will be installed on your MATLAB path, and you'll be good to go. Okay, so let's just start out, and we're going to initialize things to just get everything cleared. And we're going to load in the styles Birch 10-degree color matching functions, and that's a set of color matching functions that we can get. And just as they come in, they are at a certain wavelength spacing, and we're going to spline them so we have versions both at 1 nanometer spacing, affine spacing, and 10 nanometer version. This little notation here, S vectors specify wavelength spacing according to a Psych toolbox convention, starting wavelength, delta wavelength, and number of wavelength samples. So I create some 1 nanometer versions here using the spline color matching function from the Psych toolbox, and also a 10 nanometer version here. And then we'll just plot them. There's a little bit of plotting overhead stuff here that's from something called the Color Book toolbox that tries to make it a little more encapsulated to handle some changes to MATLAB figures. Here it's a little distracting, but I didn't take it out of the tutorial. I think there are better ways of doing this than when I wrote this, but I was not a good enough person to redo it all. So we'll just make a little plot here of the color matching functions. So here they are, and as you might remember from the previous lecture, these are not light spectra. Rather, at each wavelength, these represent the strength of the red, green, and blue primaries used in the Stiles and Birch color matching experiments required to match test light at different wavelengths. And where the values go negative for a particular primary, that means that that primary had to be mixed with the test to match the mixture of the other two primaries. So that's fairly standard. It should be straightforward, and we have those color matching functions. Now let's go ahead and get the Stockman-Sharp 10-degree cone fundamentals. We'll load those in from the Psych toolbox data file and spline them to the same 1 nanometer wavelength spacing that we used for the color matching functions. So we have those, and we'll make a plot of those. So we'll just set up a little plot, same deal, and here they are. The rather familiar shapes of the L in red, M in green, and S in blue color matching functions. These are in energy units, and they've been normalized so that each has a peak of 1. And so there those are. Great, we'll keep that plot. We're going to want it a little later. I'm going to move it off out of the way here and get it back when I'm ready for it. Now, we know from that the cone fundamental should be a linear transformation of the color matching functions. And one of the tricks, you can measure color matching functions, and one of the tricks, I would say the hard part of estimating cone fundamentals, is to figure out the appropriate linear transformation. And there are various experimental ways that have been deployed to do that. Here we just want to demonstrate that it's true, and we have both the fundamentals and the color matching functions, so we can use linear regression to find a matrix, a linear transformation, that applied to the color matching functions gives you the cone fundamentals. So we'll call this matrix M color matching functions to cones, MCMF to cones, and we get it using MATLAB's linear regression operator. There's some transposing and grouping here just to get the conventions to come out right for that linear regression, and we'll get a little 3x3 matrix, which by the conventions we've used, gets applied from the left to the color matching functions themselves, those RGB values in tristimulus space, to yield the, or at least they should yield, the 10-degree color matching functions. So if we execute this, and then we make the transformation here of that matrix, and we add these to the plot we've already made of the color matching functions, where here each of these will be plotted as a dotted black line. They better overlay or else the theorem isn't right. And you see there they are quite nicely. It's easy to see the case for the red and the green. The black doesn't show up too well on the blue, but it's there sitting right on top of the blue fundamental. So all that's working as it should. Great. So that's just a sort of, I call that a computational demonstration that this assertion that there is a linear transformation is correct, at least for these color matching functions and cone fundamental estimates. And it shouldn't really surprise us because indeed the Stockman-Sharp 10-degree fundamentals were constructed as a linear transformation of the Stiles and Birch 10-degree color matching functions. All right, now we can go on from that a little bit, and we'll just do one more thing here before we end part 1 of this video, which is we could actually go and find the tristimulus coordinates that isolate each of the cones. So imagine we wanted to have two stimuli that differed in a way that only one cone class sees them. Well, we can do that in the following way. First, let's take the fact that we know how to transform from the color matching tristimulus space to a cone space with this matrix, and realize that to go the other direction, all we need to do is find the inverse of that matrix. So now we have a matrix that takes us from a cone vector representation to a color matching function or tristimulus representation. And then the second thing to realize is that in cone space, it's trivial to know what the cone isolating directions are. We think of a stimulus as a column vector. The stimulus that isolates the L cone is one that has a non-zero number in the L cone, or the first entry, and zeros in the other two, having no effect there or no change on the M and S cone responses. So I put that as the first column of this matrix. Similarly, for the M cone, I've chosen 1. I could have put 10 there. It also would have been cone isolating, but I've chosen unit vectors. Similarly, a column vector of 0, 1, 0 here would isolate the M cones, because only the M cone coordinate would change in cone space if I go there. And finally, 0, 0, 1 would isolate the S cones. I apply this color space transformation matrix that I've derived to that to get stimuli, or directions in the RGB stimulus space that isolate the L, M, and S cones respectively. So we could check that that's true. Remember that these are tristimulus coordinates, the cone isolating durs, and we know the wavelengths of the Stiles and Birch color matching functions. We know the primaries. They were monochromatic primaries at 645, 526, and 444 nanometers respectively, to the nearest nanometer. And so here I just build up a little matrix where the first column will be the 645 primary, the second the 526, and the third the 444 as spectra. I go through each column. I find the wavelength that, here's this we set up earlier. This is a vector with all the wavelengths that's equal to the primary of that column, and I set it to 1. So this matrix B for basis 1 nanometers is a matrix whose columns represent the 3 color matching primaries used in this experiment. And again, if you watch the video on color matching functions, that idea of using matrices with the columns of matrices to represent stimuli is something I introduced there in a lecture format. Okay, so now we know the primaries, and we know the tristimulus values of stimuli that are supposed to isolate each class of cones, and so we can construct the cone isolating stimuli by weighting the primaries by the cone, the tristimulus values. So let's first run this little bit of code here to get those, and second create these spectra. So now we have spectra, and these will not be physically realizable spectra. They'll have negative power at some wavelengths because you can't actually isolate the cones with all positive spectra. But for our purposes here, we don't care about that. These are just spectra theoretically. And we could add them to all positive spectra to produce differences, or spectra that differed only by cone isolating stimuli. So now we're going to compute the cone responses to these cone isolating spectra just by taking the cone fundamentals in the rows of our cone fundamental matrix and multiplying them by the columns in the cone isolating spectra matrix. And those ought to have the feature that if we take the cone isolating LMS spectra, since we used unit vectors supposed to produce cone responses of 1, 1, and 1 in each of the 3 classes of cones respectively, this minus the identity matrix better be very small. And so let's just look at this matrix first. We'll print it out in the command window. I can get that to work. There it is, pretty close to the identity, a little off in the third decimal place. I'll come back to that in a second, but these off-diagonal entries are very small, and the diagonal entries are close to 1. And in fact, the tolerance here, the difference is slightly less than 1%. The reason there is a difference is that in the actual experiment, the wavelengths were not precisely these integer wavelengths, but as indicated up at the top here somewhere, they were a bit off from the integer wavelengths, and I didn't capture that because I'm using only 1 nanometer spacing in the code here, and so that check is good to about 1%, but not perfect. Nonetheless, the idea that we were able to find tristimulus values that isolated the cones by what we might call a color space transformation from a cone space, where those are very easy to express, to a tristimulus space where it would be harder to say a priori what those directions were, checks out here when we use our understanding of what tristimulus values are to reproduce the spectra, the mixtures corresponding to them, and then checking the cone responses to those spectra directly from the cone fundamentals. So everything is looking good. I'm going to stop the recording here, and we'll pick up in part 2 talking about chromaticity diagrams in the RGB tristimulus space and something called confusion lines or dichromatic confusion lines that are often represented in that space. This is to help us understand a little more deeply some of the ideas of cone isolating spectra as we move forward through this set of ideas. So if I can figure out how to do it, I will end the video.